Okay, so this is a little series worksheet that I thought I could do just to demonstrate some of how we approach these problems. So I did cross a few of these out because we haven't done every single type of test. Notice this mentions the root test, which we have not covered yet. Okay, so first let's look at problem number one. Uh, well, let me back up. How do I even handle these things, right? Well, this guideline really does emphasize generally how we look at these. Firstly, does the nth term even approach zero, right? So that's kind of the first question you ask. Does this look like something whose the limit of that sequence is even heading towards zero? And so let's ask ourselves, what's the limit of an? Well, that's going to be n plus 1 over 3n plus 1. And I don't know how quickly we notice this, but if you want to use L'Hopital's, you can. This is just going to turn out to be 1/3. And so because this limit doesn't even go to 0, this does not converge, so I'm just going to write that as diverges. Next, question 2. This is going to be one of our special series, right? So I don't even think about whether the terms approach 0 or not, because any time that you see something like r to the n or whatever, you're immediately going to be able to see it as a geometric series, right? Is it one of these special types? And again, sure, that's step number 2 on this thing, but for me, I immediately recognize this as a geometric series, right? Anytime you see number to the nth power. As long as it's all that's going on, then it's a geometric series with a being pi, right, the initial term being pi over 6. So yes, this converges, right? The ratio and the initial term are both going to be pi over 6. And we can say geometric series with r pi over 6 being smaller than 1, right? Because just because it's geometric doesn't mean it automatically will converge. It has to be sure that that ratio is less than 1 in size. So maybe to go straight from definition, we can say absolute value of pi over 6 is less than 1, but we know that's just going to be pi over 6, right? Okay. So, and just to be horribly clear, let me also emphasize this diverges since the limit as n goes to infinity an does not equal 0. Okay. So that's why we know it diverges. This one, we know it converges because it's a geometric series with a ratio less than 1 in size. Now, 3, this immediately looks to me like something that we can actually integrate, right? So firstly, is this geometric series doesn't look as nice as, this one. But does this look like an integral that we would be used to taking? Sure, right? If I wrote integral of x e to the negative x squared dx, can we take this integral? Yeah, absolutely. So do the improper integral u equals x squared, maybe even negative x squared if we want. And that means du is negative 2x dx. So solving for dx gives us du over negative 2x. Now plugging that in for that, our integral is now the integral from 1 to infinity of x over negative 2x e to the negative, or yeah, we let u be negative x squared, so now that exponent is just u, and we replace dx with du, and that's where we get du divided by negative 2x. So as we notice, this is just the integral from infinity to 1, negative 1/2 e to the u du, which means we get, right, the antiderivative of e to the x is just e to the x, so antiderivative of e to the u is just e to the u, and our constant sticks around. So the integral, or we'll plug in our values from infinity to 1, but remember those are our values for x. So let's put our equation back in terms of x, negative 1/2 e to the negative x squared, evaluated as x goes from infinity to 1. So that is the limit as a goes to infinity of negative 1/2 e to the negative a squared minus negative 1/2 e to the negative first. And now what is this limit? Well, a is going into infinity, which means our exponent's going to negative infinity, which means that term is going to 0. And this is going to give us plus 1/2 e to the negative first. And all we really care about is this is finite. So that means that our integral converges. So the integral test says our series, n e to the negative n squared converges to. Now don't forget, technically speaking, we should check for, is that function going to be positive from 1 to infinity? Is it going to be decreasing from 1 to infinity? But, we can save ourselves a little bit of time by just assuming that is the case, and, it is, for most of these. Any of them that we want to do the integral test on, has to meet those conditions, and certainly this is one that the only real approach that we see right away is the integral test. So, certainly. Next, what about this one? Well, this one is a little bit of an oddity, right? What do we think of when we see just some polynomial? Well, we should think, is it a p-series? And the way that it's written, it is not exactly, I'm writing this as a note to us, not as a part of actually solving the problem, not exactly a p-series, but close. Right? What's the comparison here? The p-series that we would compare it to would just be the harmonic series, which diverges. Now, are the terms here going to be less than or greater than just 1 over n? Well, 3n plus 1 is greater than n, so you're dividing by something larger, which means you are something smaller. That means that that direct comparison test is not going to help us because we know that these terms are going to diverge. So being smaller than something infinite doesn't necessarily tell you what you must be. So the direct comparison test doesn't help us here. Can we do that limit comparison test? So let's ask ourselves, what is the limit of these terms divided by these terms? Well, keep, change, flip. This turns into n over 3n plus 1. And if we want to use L'Hopital to take derivatives and whatnot, we can or not, but we see that that will be 1/3. So what does it mean if our limit gives us a finite number? That means that they converge or diverge the same. So limit comparison test. I think this is sometimes just even called the limit test. Shows that this series has the same behavior as our harmonic series, which diverges. So that tells us that our problem number 4 must diverge, since it has the same behavior as the harmonic series. So that's pretty direct, that's pretty good. What about number 5? This meets our definition of alternating. Right? Notice we have a -1 to the nth power, which means we're going to flip sign back and forth forever and ever and ever, which means we get to just do the very simple alternating series test. Well, let's emphasize, if you ignore the -1 to the n, the positive term is going to be 3 over 4n plus 1. And the limit of the bn's is the limit, as in goes to infinity, of 3 over 4n plus 1. The numerator is staying constant, the denominator is getting infinitely large, dividing by something becoming larger and larger and larger. This heads to 0. So technically we also want to see, right, the derivative being negative to say that these terms are going to get smaller. We want bn plus 1 to be less than bn. Can we see that that's happening? As n increases, our denominator increases, so n plus 1 must be smaller because it has a larger denominator. Absolutely. You can write that out if you want. You can say the derivative of 3 over 4x plus 1 should be oh, sorry. 3/4. Right, take the 3 out of the numerator, take the 4 out of the denominator. I forgot to write the derivative symbol. I was trying to say let's just factor that out from the derivative. And now maybe we can see a little bit more clearly what this derivative is supposed to be. Right? I say maybe. 3/4 derivative of x plus 1/4 to the negative first. Subtract 1 from the power, or sorry, bring the power down, subtract 1 from the power. So -3/4 times x plus 1/4 to the negative second. And technically that's a chain rule, but what's the derivative of the inside? Just 1. So we're happy with that. Now the question is this going to be negative? Well, notice the denominator is squared, so the denominator will always be positive. Positive times a negative will always be a negative. So yes, this is decreasing. So yes, this fits the conditions required for the alternating series test. So Bn is decreasing. So the alternating series test says our series converges. Again, maybe, solving these is a lot easier than actually writing out like why, what happens. But that's a challenge oftentimes. Right, that's a difficulty in math sometimes, is having to justify your work. But that's an important step. So don't forget it. Okay, here we can immediately tell, oh, this is written exactly how we write a p-series. But what is p? 3/2, right? What's the power that you're raising it to? The 3/2 power is greater than 1, so it diverges. Wait. No. Oh, I have it backwards. I have it backwards. The p being greater than 1 means it converges. I will not edit that out because y'all need to see that I am still human. Ultimately, right that moment, let's check ourselves and make sure we remember how this is written. If p is greater than 1, then we converge. Excellent. This series, first, do the terms even go to 0, right? This is one where it's written out a little bit oddly, so let's just even see what is the limit as n goes to infinity. It's not an easy integral to take. We don't see a simple ratio, so let's just see what does the limit look like here. N squared, 2n squared plus 1. Oh, use L'Hopital. I keep saying use L'Hopitals if you want. What would that look like? 2n over 4n plus, oh, sorry, derivative makes that disappear. So 2n over 4n, which is 2/4. So the limit of this is 2/4, not 0. So this diverges. Nice. This one, I noticed this looks a whole lot like a p-series, where p is 2. So how can we compare it? Well, note that 1 over n squared is going to be greater than 1 over n squared plus 5, right? N squared is less than n squared plus 5, so this means we're dividing by something larger, which means our terms look smaller. So I'm skipping a step, I guess, and by saying that we recognize that this is a p-series which converges, or you do the integral test if you want to go that far. P is greater than 1. So the direct comparison test says that this series converges as well. Converges. Nice. This one, this is a pause, as I would do in class if I was staring at y'all waiting for someone to say something. This we see as a ratio, right? So this is a geometric series. But what is our value for r? Well, that is, what we see in the parentheses, e divided by pi, which e is about 2.6 or 2.7, I don't remember. And then pi is about 3.14. So something less than 3 divided by something greater than 3, that is less than 1. So it converges. (13) is a very interesting problem. The way that it's written, it looks like it's going to be very messy. But note that cosine of m pi is something that we're going to be able to simplify very easily, very directly, right? Because if n starts out at 1, for instance, that's going to be cosine of pi, which is if n is odd, cosine of pi, cosine of 3 pi, cosine of 5 pi, right? That's where we're straight up, or sorry, all the way across in the unit circle, which means we're going to be -1. If n is even, that's going to look like cosine of 2 pi, which is going to be +1, perfect. So really, we can write cosine of m pi over n as -1 to some power, because all it's doing is flipping back and forth between -1 and 1. So how would we want to express it? We want to make sure that the even and the odd pieces match, right? So when you plug in 1, we want to get -1. So we can do it just like this, right? When you plug in 1, you want to get exactly -1. So that fixes it, right? Okay, so now we can see that this is actually just the basic alternating harmonic series, which we can say do the limit as n goes to infinity of 1 over n equals 0. And we know 1 over n plus 1 is less than 1 over n. So alternating series test. Says it converges. And very subtly, again, does it converge? Absolutely. We'll take the absolute value of this thing. You get back the regular harmonic series. No. So technically this converges conditionally. This is conditionally convergent. But we weren't asked that, so we'll just say it converges and stop there. All right? Okay. I definitely meant to cross this one out. We don't want to look at factorials right now. And this one, I want to look at this. We see this, and right away it looks nasty. Anytime that the expression starts to look gross in a way that it looks way more complicated than what a series typically looks like, that's kind of a cue that it could be something that we're meant to integrate. So can we integrate? I don't know why I wrote n again. Can we integrate something that looks like this? Well, hopefully there's a basic substitution. What's the issue here? Well, the exponent here and having this in the numerator are both kind of their own special problems. Is there a way to fix them both at once? Yes, absolutely. If you do the u substitution, u equals x squared, then du is 2x dx, which means dx is du over 2x. So this integral becomes the integral from 1 to infinity, e to the u, and then dx is now du divided by 2x. So our integral, we can pull the 1/2 out. X divided by x cancels. So this is 1 over e to the u du. And don't forget, having that in the denominator is the same as just having a negative exponent. I forgot to write 1 into infinity. So this is just e to the negative u du. And we did this a little bit ago, I think, right? -1/2 e to the negative u. Evaluate as x goes from 1 to infinity. So let's get this back in terms of x. E to the negative x squared from infinity to 1. And we can recall this actually goes to, what's it going to be? 1/2 e to the negative first, which is finite. So our integral converges. Thus, the series does as well. And again, technically speaking, do all the checks involved with the integral test, but we're kind of skipping that for right now to save some sanity. So this converges by the integral test. Okay. And that's where I'm going to stop right now. We are going to be able to handle problems like 7 once we get the root tests, which is actually going to make this problem relatively straightforward. Yeah. Okay. And the others as well. We'll figure out how to handle those later. And we'll tackle those again when we're maybe more comfortable with it. Okay. Yeah. Goodbye. Have fun.